let's get started by talking about what happens when things get bigger. We'll define the percent of increase. The percent of increase is how much something got bigger over the initial amount. Now, if you look at the how much something got bigger over the initial amount, that would be basically a fraction between 0, if it didn't get bigger at all, over the initial amount, up to the initial amount itself. So you would have a fraction that went between 0 and 1. To convert that fraction to a percent, we multiply by 100%. So for example, if the initial amount were 10 and it got bigger by 5, we would have 5/10 or a half times 100% or 50%. It doubled in size basically. Its percent of increase is 50%. Let's look at another way of talking about the amount of increase. The amount of increase is how much it's changed. In other words, you take the difference between the new amount and the initial amount gives you that amount of increase. So when we talk about that, that's the change in the size divided by the original size of whatever the quantity is. Remembering this definition is important because we're going to use the ideas in this definition throughout the rest of this unit. And in fact, it's going to be a piece of a lot of what we talk about in units B, C, and D as well. Let's take a look at percent of increase a slightly different way, and let's relate it to what we've learned in class 12. We've seen, if you remember, that a percent of something times the whole thing is equal to the part of the thing. We can look at percent of increase in the same way. The percent of increase, which is equivalent to the percent we talked about in class 12, times the initial amount, in other words, the whole in class 12, is equal to the amount of the increase, which is the part. So the percent of the increase times the initial amount is equal to the amount of the increase, which is, in a way, if we look at the original definition algebraically, is a way of just working it a little bit backwards. Again, we can continue to look at it a little bit differently, and we now say the new amount, how much we get to, is equal to the old amount plus the amount of the increase. We have all of these different interrelated relationships that we're going to use looking at percent of increase. Now let's plug some numbers in just to see what happened. How often has something like this happened to you? I know it's happened to me at least once. I remember I was getting my car repaired. I walked in and they said, "Oh, we're sorry, your bill is going to be $100 more." And while I didn't look like that at the time, I remember fuming and my face turning red exactly the same way. Let's see what a $100 increase might mean. And we're going to start with that original definition. The percent of the increase is the amount of the increase over the initial amount. Well, suppose my initial bill was $200. Then I could calculate $100 more added to that. That's the amount of the increase over the initial amount. So I have the $100 more over 200. And all of a sudden, I'm talking about a 50% increase. But suppose I have that same $100 and my initial bill, instead of being $200, is now $2,000. So I have $100 over 2,000, and now instead of a 50% increase, I have a 5% increase. So you see, you can take the amount of increase, and the percent of increase depends very strongly on the initial amount. So suppose I paid $2,000 for, say, a new couch, and all of a sudden I find out it costs me $100 more. Well, that's okay. It's not as bad as 50%. It's only 5% of that $2,000. Now, suppose I bought a new car, and then all of a sudden found out I had to pay $100 more on that. I'd hardly think about it, because if I started to look at that and do the calculation, I would only have a 0.5% increase. And so the point of all of this is that you can have a certain amount that the thing increases by, and depending on what the initial amount is, the percent of increase is relative to how much you start with, and then as the amount you start with gets bigger and bigger, if the amount of increase stays the same, it makes, or seems to make, less and less difference. After all, what's $100 out of 20,000 compared to $100 out of 200? The best thing we can do to see how this works is to look at an example. If the sales tax on a $45 blouse is $3.15, what's the percent of increase in the price of a blouse? In other words, you can consider the sales tax that you add to something as a percent of increase that's going to make the tax on it, or the ultimate price on it, bigger. Let's look for the information that's in this problem. We have a $45 blouse with a $3.15 tax, and what we're looking for is the percent of increase of the price. Let's summarize the information. There is what we're given, $45, $3.15 tax, and we're asked what is the percent of increase, or another way of looking at it is what's the sales tax. And of course, it's usually good to make yourself some kind of a diagram to show what's going on. There's the 100%, the $45 that we know we're going to pay for the blouse, and then there's some increase on top of that that we're going to be paying more than that initial $45. We want to know what the percent of increase is. We'll start with the original definition for the percent of the increase. It's the amount of the increase over the initial amount. We'll substitute in what we're given for that, the $3.15 increase over the $45 for the original cost of the blouse. And when I figure that out as a fraction, it works out to 0.07. Then if I multiply it by the 100%, I get that 0.07 times 100% is equivalent to 7% sales tax. We also now have to look at the final price increased by that 7%. The total bill, what you pay, is the price plus the tax. I would add that in, the $45 plus the $3.15, and all of a sudden that blouse cost $48.15. Another interesting thing that you might look at is that the $48.15 is 107% of the $45. We have the 100% from the original $45 plus the 7% sales tax. So if you multiplied 45 by 1.07, you would get an answer equivalent to adding the tax to the price separately. I just wanted to point that out. That sometimes makes things a little bit easier. If you know there is a 7% tax, instead of calculating the 7% and then adding it, you can just add it right to the percent and do one calculation. Let's check. We got as an answer 7%. To go back, let's ask what's 7% of 45? If we do that, we get $3.15, which we're given. That tells us that 7% is in fact the answer, and we've done this problem correctly. Good for us. Here's something I came across when I was looking through the paper. Not, unfortunately, the Arizona paper, but a paper. I found that the governor is to raise pay levels of state employees by executive order, and the plan will raise the entry-level wage of all pay grades an additional 7.4%. Boy, that would be wonderful. Let's look at that as a problem. What is the new salary for a worker receiving a wage increase of 7.4% if the starting wage is $8 an hour? We're looking at this from a slightly different point of view, because now instead of being asked for the percent, we're given the percent and asked to find out what the new increased amount is using all of our definitions. Let's mine this problem for information. We want to know what the new salary is. We're given the percent of increase, and we're given the initial amount. Here is what we're told. We're given that we start at $8 an hour. We increase 7.4%. We're asked for the new wages. Again, some kind of a diagram doesn't hurt anything. What we want is, as you see there, the new amount, the $8 an hour, plus that 7.4% increase. Let's calculate that now. We remember that the percent of increase times the initial amount is equal to the amount of the increase, so let's go after that first. We have 7.4% times $8, but we can't use 7.4%. We need to change that to a decimal. In order to do that, I change 7.4%. Remember, you move the decimal point 2 places to the left and get 0.074 as the decimal equivalent of 7.4%. Now I can do the multiplication, and I find out that amounts to an extra 59 cents an hour in wages. The new hourly rate then is the original $8 plus the 59 cents increase, so now someone who was originally making $8 an hour would be making $8.59 an hour. Now, the old amount plus the amount of increase is equal to the new amount, and again, the $8 plus the 59 cents is going to give me $8.59 as that new rate of pay. Let's check this. And we can do it by seeing if, in fact, 59 cents over $8 times 100 is going to yield 7.4%. And when I get my calculator and do the math here, I find out, yes, indeed, this does work out, and I've done this problem correctly, and I can move along. Let's look at this from a different angle. What we've done so far is we've calculated the percent of increase. We've calculated the new wage from the old. In other words, we've calculated the increase. And in this problem, we're asked to come at it yet a different way. Let's see what we're given here. We see that Julia received an 8% raise this year and now makes, in other words, the final salary is $28,000. What we want to do now is work back to the original salary for this percent of increase. Reviewing again, there is the information. She's making $28,000 a year after her raise. And what we would like to know, what we want to do, is work backwards to find out what the original value was. Here is a diagram. What we want to find is the old salary. We know we have the new salary, and that includes an 8% increase. Let's let F be or represent the amount of her former salary. We don't know that, but we can use the definition. The new salary is the old one plus the increase. Let's do this. The old salary is F. Then we know that the increase is the percentage increase times the old salary. 8% expressed as a decimal is 0.08. So her new salary is F, her old one, plus 0.08F. I notice here that I can say it's 1F. Remember, F is equivalent to 1F. And I see I have F in both of those terms. That means that I can factor the F out. I can go the opposite way using the distributive rule and do this. Her new salary of $28,000 is the quantity 1 coming from that original quantity in green plus the 0.08, which comes from the increase times F, or $28,000 is equal to 1.08 times whatever the original salary is. Remembering that, this is what we had from the previous page. Now you notice that equal sign's a little funny, and the reason is this. I'm going to divide both sides of this equation by 1.08 to get F by itself. When I do that, I find that F is 25,925.93 to the nearest hundredth, or her former salary is $25,000, and let me just round that off, 926. Her former salary is $25,926. Let's check that. We'll take the former salary and get 8% of that, and then add that to the former salary. In other words, the original plus the amount of increase is equal to the new amount. I find that this works out, and I am satisfied that I've done this problem correctly. Take a look at one more here. Here is some information that I got from the Pima College website about enrollment. It said the actual enrollment in the first semester was 18,027 students. Budgeted for spring, we have 19,400 students. What percent of increase is assumed here? There is what we're looking for. Here's what's given. And incidentally, if you see the word FTSE, we call that in the education business FTSE, and it stands for full-time student equivalents. In other words, if you look at all the students we have and then look at how many of them are taking about 15 units, divide that out, you get full-time equivalents. Anyway, the point is that we have 18,027 in the fall. We're budgeting for 19,400 in the spring. What is the percent increase? There is a diagram that shows what the situation is. Let's work on this. The percent increase is the amount of increase times the initial amount. The amount of increase, we get the new amount minus the original amount. Plugging that in, we find that's equivalent to 0.076, or 7.6% increase. So we're budgeting for a 7.6% increase. Let's check it. What is 18,000 plus 7.6% of that? If we work that out, we find, in fact, it's 19,400, and we've done this correctly. Well, we've dealt with increase. Now let's take a look at decrease. And again, it's the very, very similar thing, except now, instead of something getting bigger, it's going to get smaller, meaning that the amount you have when you're finished is less than the amount you have when you begin. we see that the percent of decrease times the initial amount going the other way is equal to the amount of the decrease. Something similar to what we had before. And again, we can look at this as we did before. The amount of decrease times the initial amount, the percent of the decrease times the initial amount is equal to the amount of decrease, the same way the percent times the whole is equal to the part. The only difference between percent of increase and percent of decrease is right here. Instead of adding the amount of increase, we subtract the amount of decrease from the old amount. Otherwise, we operate in exactly the same way. And one thing we can talk about in terms of how this works is discounts. If I have a $45 blouse that's on sale for $25, it's been discounted, and what we want is what's the percent of decrease for this sale. There's the information we're given and asked for, and we can summarize that. There's the information we're given, here's what we're asked for, and what we want to do now is calculate the percent of decrease. In order to do that, we first need to find out what the amount of the decrease is. Remember, the amount is the initial amount minus the final amount is going to be the amount of the decrease. The initial price minus the sale price is how much it's decreased in price, $20. I plug $20 in there and find out that that blouse has been discounted 44%, or that I have a 44% decrease. Let's check this problem. What is 44% of $45? It should be $20, the percent of decrease. When I do the math, take 0.44 times the 45, I notice something interesting. I don't get exactly 20, I get 1980. And the reason it doesn't exactly equal 20 is because when I got the 0.44, if I looked at my calculator, it wasn't 0.44, it was actually 0.44444444444444, one of those things, and I rounded it off to 0.44. So then when I went back to calculate this backwards, because I killed all those other fours and all the other decimal places, I didn't get exactly the same answer, but close enough for rock and roll. And what this did was made me go back and think about what was going on. Now, let's look at another kind of percent decrease. We'll talk about a discount. And here is a definition of discount. It's an amount subtracted from some price. In other words, the store discounted an item by 10%. So we can talk about discounts as being a percent of decrease. A 25% discount applied to a $70 camera. What's the final price? There's the information. Summarizing the information, we have a $70 camera original price at a 25% discount. We would like to know the final price, and here is our diagram. We have the whole thing. We know what the decrease is, the 25%. What we want is the new price, what we're finally done with. We're going to start our analysis here. The percent of decrease times the initial amount is equal to the amount of the decrease. We'll find that now by plugging in the numbers. 25% of 70 is 0.25 times 70. That gives me $17.50 when I work that out. That's not the final price, that's the decrease. To get the final price, I take the initial price minus that $17.50, and I find that the final price for my camera is $52.50. Now there's another way I could do this. I could say that the discounted price is the original price minus the discount. Now, the original price is 1 times whatever the price is, minus the discount, which is 0.25 times that original price. Doing some math, I find that I could just find the discounted price by taking 75% of the original price, and I would wind up with exactly the same thing. In other words, you pay 100% minus the discounted percent of the item. So 100% minus 25% is you pay 75% of the original price of the item.